Alright, hi everyone. I'm going to be presenting on Game Boy reverse engineering. So first, just a quick introduction. Um, so my name's Claire Seiler. I was the president last year from fall 2020 through spring 2021. I'm currently working out in Albuquerque, New Mexico as a security researcher at Sandia National Laboratories. So some of the things that I focus on with that work is emulation, some vulnerability research, hardware, and formal methods work. So if you have any interest in any of those things, feel free to shoot me a message and um, I can talk about what I do and maybe help align you on a path to one of those topic areas. So, my Discord handle is Comrade, so you can feel free to ping me about security stuff, or if you share some of the same hobbies, uh, you can go ahead and reach out to me for that. So I just have some photos on the right of mainly Albuquerque, so that's the top left and the bottom left photos are from Albuquerque, and then top right is from graduation, and bottom right is a picture. I went climbing with some buddies out in Jemez, so I'm hoping to do a little bit more climbing once my shoulder heals up and get on some harder routes. So, just as a background, Game Boy refers to a line of different um, handheld electronic devices, gaming systems, created by Nintendo. So most of you are probably familiar with Game Boys, and many of you may have had one growing up, or even have one now. So there's been a line of different Game Boys, different models. Today we're going to be talking about the original Game Boy from 1989, and that's in the top left corner. So that's the one that doesn't have color, it doesn't have uh, advanced backlighting. It's the simplest architecture, and it's I would say the easiest to reverse engineer. So it's a really good starting point for getting to know Game Boys. Um, the others are pretty similar, but there are some major differences because, like, with the Game Boy Advance, they actually use a whole different CPU. They use an ARM-based CPU, and we'll talk more about the differences. Um, but yeah, today we are going to be focusing on that 1989 original Game Boy. So, like I said before, we're only going to be focusing on the original Game Boy architecture. So this architecture consisted of an 8-bit CPU, and so the architecture, the instruction set isn't going to be too difficult because it is designed for an 8-bit CPU. So I just have some more details about the internals listed here. What you really want to focus on from this is that the RAM was 8 kilobytes. ROM sizes depended on the cartridge size, so it could be 16 kilobytes, 32, all the way up to 4 megabytes. So the cartridge size dictates how large of a game you can have. We're not going to be diving too much into sound or anything, but we will have a little bit of discussion about graphics. So, with the original Game Boy, it did support 4 different shades of gray, so it wasn't actually supporting color at that time. And it could display up to 40 sprites at a time. I'm not going to go into like the DMA controller or how interrupts work on this architecture, just for the sake of time. So this is a pretty detailed pinout of the Game Boy architecture. This is more just for your own reference if you find it interesting. So you can see, like with the Game Boy cartridge, what those pins in that cartridge actually mapped to. So that's really helpful if you wanted to dump your own ROM. And then just a quick little side note about legality. Um, Emulation is legal, so if you ever wanted to write your own Game Boy emulator, that's perfectly legal. The issue rises when you start downloading ROMs from websites. That's where you run into copyright law issues. So, um, if you wanted to test your own Game Boy emulator or test someone else's emulator, you would have to either make your own ROM or dump a ROM from a cartridge you already own. So I just wanted to make that distinction clear because I don't want anyone to get really excited about this work and then find themselves in some legal trouble because they weren't sure what those boundaries were. So to dive into a discussion about the CPU, I mentioned that it was an 8-bit CPU. It's a cross roughly between the Intel 8080 and the Zilog Z80. I'm not expecting anyone here to be familiar with those processors, but if you are, that's awesome. You'll catch on much faster. So the CPU runs at 4 megahertz. That's going to be significantly slower than any CPU you have running in your laptop or your desktop, which generally is going to be around 2 to 3 gigahertz. So emulators have to kind of take that into account and scale down the speed of execution. The specific CPU we're focusing on, the Sharp LR35902, supports a variety of standard types of instructions like load instructions, arithmetic operations, logical and bitwise operations, CPU control, jumps, calls, returns. So if you've looked at any type of assembly, a lot of these instructions are going to look pretty similar. If you haven't been exposed to assembly previously in any form, then these mnemonics may be a little confusing. I'll kind of walk you through an example where I explain what the instructions are doing and then show you both a disassembled section of code and a decompiled section of code using Ghidra. So if you don't understand what all of these mean, that's totally fine and totally expected. I'm just kind of laying out an overview of the instruction set architecture for those who do have a familiarity with assembly. So continuing the discussion, the Game Boy original supports 8 general registers, so that's A, B, C, D, E, H, L, F. I don't know why they didn't want to make it a little bit more consistent with the naming conventions, but it is what it is. So you can combine those 8-bit registers to form 16-bit registers. You can only combine them in those listed configurations, like A paired with F, B paired with C, D paired with E, and H paired with L. You can't mix and match. That's just not how it's designed. So you can read from and write to them, so you can use them to store any data that needs to be stored during the execution of a program. And so the F register holds flags that give some information about current conditions. So like if you have a compare operation, generally that's going to set like the 0-bit based on what that compare comes out to. So there are two special purpose registers. So there's the program counter, and so with any assembly language, you need some sort of um, way to keep track of what instruction you're currently executing. So in this instruction set architecture, that's dictated by the program counter, the PC. Then the stack pointer will point to the top of the stack, and then if you haven't previously attended like a reverse engineering talk or are familiar with stacks from data structures, a stack is just a way to keep track of memory. Um, so I can go into more explanation offline, um, but I'm going to kind of gloss over it and assume you know what a stack is. If that assumption is um, not a good one, then I can provide additional clarification. So it's kind of hard because I'm recording this and I'm not in person with you guys. I don't know what, I can't get any feedback on what your familiarity is with certain topics. So, yeah, feel free to ping me offline if you need more info. So, with the instructions, so say like a load operation, you would list the destination first and then the source. So if you're loading something from uh, one place to another, like one register to another, you would list the destination register first and then the source register second. Um, and then you can load data in a variety of different ways. So you can do immediate loading, where you're just transferring a value directly into a register. You can do indirect loading, where you're loading the contents of a register into another register. You can do stack loading of registers, which means you're just popping a value off the top of the stack, and then you're storing that value in the corresponding register that you list. And then you can also load register contents directly to a memory location. So I have examples of all four of those types of data loading, and it should look familiar if you've done anything with x86. So one of the most important things to know when you're working with a Game Boy is knowing where everything is mapped in memory. So this is a fantastic diagram that kind of lays out your different sections of memory and what they correspond to. So from 0000 to 7FFFF, that is going to correspond to the space that you use for your ROM. So basically, if you have a 16 kilobyte ROM, that's going to get stored in 0000 to 3FFFF. If you have a 32K one, it's going to get stored from 0000 to 7FFFF. So that corresponds to that fixed home and home region. And one thing to note is that when you load your cartridge, there is some like set amount of data. There's a certain number of ROM instructions that always have to be present to basically get the Game Boy into a state where it's ready to play the game or load any further data. So it's basically setup information. And that's also where like that Nintendo logo pops up, is in that kind of like initial setup period. So that has to be present in every cartridge. So it has setup and it has copyright stuff. So that's just useful to know. Then you also have your different RAM sections. So you've got like your VRAM or your display RAM as it's described here. Expanded work RAM, I believe that's also corresponds to OAM, but I could be wrong on that, so don't hold me to that. And then there's the internal work RAM. So these RAM sections are used for different parts of like mainly for graphics. So the RAM sections are mainly used for graphics, but it also holds other data as needed. So this is another diagram that is useful to get an idea of how memory is laid out. So you've got your cartridge header area, which I described. That's at hex 100 to hex 14F. Restart and interrupt vectors, those are basically defined in the area from 0000 to 00FF. And then that's part of the ROM, and that ROM section can go from 0000 to 7FFFF. Then character RAM, which is like sprite information, that's going to be 8000 to 97FF. Then background data for graphics, so your background, all of that is, so you can have two backgrounds defined at the same time, but you can only have one loaded. So background 1 is at 9800 to 9BFF. Map 2 is 9C00 to 9FFFF. Then if the cartridge needs additional RAM space, then you have it in that next section. Then there's internal RAM, which is basically set aside RAM that is mapped from the cartridge. Or, sorry, I may be misspeaking there. But you can have up to 8 banks. Bank 0 is always going to be there from C000 to CFFF. Then bank 1 through 7, they can be switched in and out, and they're in that next section. OAM, object attribute memory, is used for sprite data. So that's at FE00 to FE9F. For hardware I/O, so that's your user input. So like if you're sending button presses to control your character, those registers are in FF00 to FF7F. So those registers will hold the state of those buttons. Then there's interrupt flags and other miscellaneous. So that kind of gives you an overview of how this memory is laid out. So jumping into graphics, the Game Boy has 160 by 144 pixel resolution display. It uses just ARGB values and only supports 4 colors. And those 4 colors are white, light gray, dark gray, and black, so not too colorful. But it at least gives some differentiation. Then, like I said before, some of that graphical data is located in the OEM memory space, as well as the VRAM. So the way that graphics work in the Game Boy is that you've got sprites, you've got backgrounds, and you've got windows. And so sprites are basically tiled onto the screen, and then they overlay on top of window tiles, which then are like loaded within a background. So that may be a bit confusing. I'll try and make it a little bit more clear when we actually start going through an example. So there's a couple different registers that control how visuals are rendered. So there's the LCD register, scroll Y, scroll X, scan line, and current palette. And so, like mentioned before with the LCD register, it controls what gets rendered. So you can use it to enable or disable the display, select the window tile bank, enable window and sprite displays, and other things. So, like mentioned before, there's a background which is composed of a 32 by 32 matrix of tiles, and each tile is 8 by 8. So you can have a total resolution of 256 by 256. And if you remember before, we said that the display was 160 by 144. So obviously a full background can't fit onto a 160 by 144 pixel screen. So you have to do some scrolling. So that's controlled by the SCX and the SCY registers. So when you're moving a character while you're playing a game, you're causing the SCX and SCY registers to change by moving your character past the edge of the screen and causing it to scroll with your motion. So backgrounds are located in the background tiles are located in the background tile map VRAM section. So you can have 2 background tile maps stored at one time, but you can only display one. And so the window overlays directly on top of the background, and this does not scroll. So the background scrolls, but the window does not. And it's positioned with the window pause X and window pause Y registers, and you can enable it or disable it depending on what you're trying to display. And sprites are 8 by 8 tiles that are overlaid on top of the window, and so they're stored in that OAM sprite table RAM section. Each sprite has its own color palette, so you can switch out the colors. It's not very significant with the original Game Boy, but with Game Boy Color and Game Boy Advance, those color palettes get more important because you can get a lot more color because it only supports 4 colors in the original. So there's various parameters that are associated with sprites like position, priority, orientation, and size. And by priority I mean when you're layering sprites on top of one another, which one should take priority, which one should be at the top. So users can direct input using the Joy P register, so that's the joypad. So that register will hold values for that start button, that select button, A and B, and also the directional pad. So anytime you click a button or change the direction of your character by clicking on the directional pad, an interrupt int 60 is set, and so the CPU has to go then address that interrupt, and then interrupt vector will correspond with that, and then it'll execute a handling routine and then return execution back to the CPU for the program execution. So that was a a quick overview of the Game Boy architecture. I know it's kind of dry, but it is useful information for trying to understand what you're looking at. I think this is where it's going to start getting a little bit more interesting and more tangible for you, is once we start getting hands-on with that. And so to do that, you can use a variety of disassemblers and debuggers or emulators. So the one that I'm going to be using is Ghidra and the Ghidra Boy plugin, along with the MGBA emulator. I will also show the BGB emulator, and maybe if time permits, I'll show one of the others. I would recommend using Ghidra as your disassembler. You can use R2, Binary Ninja, IDA Pro, or MGB Dis. IDA Pro, you do need the Pro version for this architecture, but I think there's better alternatives for the Game Boy architecture. I think Ghidra plus that Ghidra Boy plugin does a pretty good job. So patching Game Boy ROMs can be a little bit tricky. So sometimes it just doesn't work because of the ordering of ROM sections in the binary. And so I listed a script that should actually help with that if the order of the ROM sections is impacting your ability to patch ROMs. So these are the challenges that you can practice with. So these are from past Capture the Flag competitions. I would take care when searching for some of these. I think the Hackloo 2014 one, there's some sketchy site that if you visit that CTF write-up to try and get that Game Boy ROM, it will take you to some pretty malicious, sketchy site based out of Russia. So just a heads up, take care when you're trying to fetch these files. I'll have some of them ready for you, like the Turing Agent ROM. So you'll have some that you can work with and won't have to troll the internet for. And then I listed some of the write-ups that are pretty helpful for understanding how these challenges work and how they can be solved. I recommend trying it on your own before you read through a write-up, because half the fun is beating your head against the wall trying to solve something, and then eventually making a breakthrough. So reading a write-up is awesome for helping you understand what you got stuck on or what you didn't know, but it does take away some of the fun if you don't put like tons of hours in and then finally get a breakthrough and get the satisfaction of completing it yourself. If you wanted to make your own ROM, which I recommend if you're going to make an emulator or something like that, you can use a tool called Gameboy Studio, and it will make it much easier to design a game because it has a drag and drop interface and a block style scripting engine, so very similar to Scratch, and so it makes it significantly easier to design Game Boy ROMs and use them for your own testing. There's also RGBDS, which I haven't used before, but it has its own assembler, a linker, a header fixer, and then a graphics converter to convert PNGs to Game Boy graphics. And on that end, you can also use tile mapping software to design your own sprites and map them to Game Boy compatible sprites and tiles. And so sometimes you can just directly convert it, but other times you need to do some resizing or actually tile from scratch. So here's some more resources. Pandocs is going to be your best friend for understanding the instruction set architecture, how things work within the Game Boy, how it handles graphics, sound, interrupts, you name it. Pandocs is kind of the supreme source. If you want to understand the hardware more, you can follow that link. If you want to know how Game Boy programming development works and make your own ROM, you can look at that link I have listed below. So now I'm going to go into some exercises and kind of walk you through how you would solve a Game Boy reverse engineering challenge in a Capture the Flag competition. I will walk you through how to use Ghidra and Ghidra Boy and then BGB to solve this challenge. And then that should give you a pretty good starting point for solving additional challenges, especially those other CTF challenges that I included in the slides. Alright, so I'm going to load up Ethereal Boy, which is this game.gb ROM, and I'm loading that into BGB. So I basically have control of this little character, and I can move around the screen. There's one other sprite, which is this man, so I am pressing the A button when I get close to him to see if I can talk to him. Every time I hit that A button, I see some character sequences printed to the screen. So I'm not sure what these mean. They look like hex values, but there doesn't seem to be a particular pattern to them, and they seem to be changing quite a bit. If they were repeating, I would say maybe that's the flag, but they don't seem to be repeating. So looks like we're going to have to do some further digging to try and figure out how we get the flag. So we can leverage some of the tools that BGB comes with. One of the tools is a debugger, and then another one is a VRAM viewer, so you can look at the visual data. Then also you can get information about the cartridge that you have loaded, and then system info. So if you look at the cart info, you can see this is a 32 kilobyte ROM. This is a Game Boy original ROM, so it's not designed for Game Boy Advance or anything like that. And then system info just tells you like what graphics libraries you have. So let's go ahead and take a look at the VRAM viewer. So we see the background. So as we were talking before, you have the background, and then you've got a window, and then you've got sprites. And all of those are made up of tiles. So this is the background, and you see it's made up of all these tiles. And we can see how this maps. So this is our total possible background, because remember, it can be bigger than our actual display, and it can scroll. This is the part that's displayed. And then we can go ahead and look at tiles. And when we look at tiles, suddenly we see something interesting. We see the flag. So, in addition to seeing the tiles that make up our character sprites and make up the background, you also have this flag under the hood. That's the whole goal of the challenge, is to find that flag. So we've done it by looking at the tiles in VRAM. And then we can also look at OAM just for increasing our understanding. So this is basically just saying the location of the tiles that make up sprites. So we have two sprites on the screen, which is our character and the other character. And these are some of the tiles that make up those sprites, and you can see the x coordinate, the y coordinate, what number of the tile corresponds to, OAM address, and then tile address. And then if you wanted to flip it, this could be set. If you wanted to flip it the other way, that could be set. You can see the priority and then also the palette. And so these are the palettes. So every sprite or every tile you can change, or sorry, every sprite you can change the palette and define a palette for it. With the Game Boy original, that's not too exciting because you only have 4 colors to work with, but you can change the ordering of those colors. So you can make this guy's hat the lightest color versus the darkest, and so on and so forth. But yep, that's it. We finished the challenge. I'll just show you the debugger because it comes into it becomes handy for other challenges. So basically, you can see what's in ROM. You can also see your registers up here and the values as you're going through it. So you've got your general purpose registers here, AF, BC, DE, HL, and then you've got your special registers, which are the stack pointer and the program counter, and then you've got some of your control registers that are used to control like visual settings like LCDC, and yeah, you've got some others that I'm not going to go into for the sake of time. But yeah, you can look at your working RAM bank. You can look at your HRAM, your I/O, and your ROM. So this is just a good reference to have. And you can also step. So if we want to step over, we can just keep doing that. And so these are the instructions as they're being executed. So since we're not actually changing anything with the control of the character, this is all general Game Boy handling routines that happen in the background. This is not anything active that the user's doing, like changing the direction. So you'll see that these routines tend to repeat themselves because the Game Boy is basically either waiting for an interrupt or it's pulling different addresses in memory to look for updates. So that just gives you kind of an introduction to it. You can also log the executed instructions. You can look at the joypad window. There's a lot of other stuff you can look at. I/O map. So you can see the visuals, what registers are controlled, or what registers control various aspects of the visual display, sound, timers, DMA, so on and so forth. Yeah, so like most debuggers, you can single step instructions, so you execute them one at a time, or you can just continuously run, and so this is continuously running, so you're not executing the instructions one by one, you're just executing all of them as they happen in real time until you hit like a breakpoint that you set. And we haven't set any breakpoints, so we're not going to hit any. You can also step over, so that way you're single stepping, and then when you get to a call instruction, you step over it, you don't go into it and execute that subroutine. Yeah, there's you have the ability to change the values in the registers, so you can control the program execution by changing the value of the PC register, which may mess up other things, but it's useful for just debugging if you don't really care. You can also toggle breakpoints and have the breakpoints be set for certain expressions. You can search for strings. You can save your current memory state out as a memory dump. There's a lot of different options that you have, but those are kind of the most useful. So that's just a quick introduction to BGB. So we'll go ahead and move on to the next challenge then. Okay, so I'm importing this this Game Boy ROM, so mission.gb, and then I'm renaming it because I already have it disassembled and uploaded. When you upload it, if you don't have Ghidra Boy already incorporated into Ghidra, then you will probably see something different on this import results summary screen. I will be staying on after the meeting to help anyone configure Ghidra Boy if they want to get it configured. So don't fret if you can't follow along perfectly. I will be staying longer to help out. So you'll get a bunch of information, and you can see that some of the stuff we talked about is identified by Ghidra. So that address size, it's 16 bits. So we can see it here. That Ghidra was able to understand that, and then it understood that it's got like little endian, and then that CPU. The acronym isn't exact, but basically it's saying it's a sharp CPU. So then it talks about how many bytes the memory took up, and then we see that address range, and it corresponds to what we would expect a Game Boy ROM to occupy, so 0000 to FFFF. So this all looks great. It looks like it imported it correctly, it identified it as Game Boy, and we're good to go. So we can just hit OK. And then we can pull up that file. So double clicking will launch the code browser. And then we've got some analysis options. You can pretty much keep it as default, but I'm also going to hit decompiler parameter ID because it'll help, it'll like list parameters to functions in the decompiler window. So if it identifies parameters successfully, it will list those. So here's what I mean by you have to painstakingly manually tell Ghidra to disassemble. So you see all these question marks. That means it doesn't know what instruction it is there. So it already finished its auto analysis, but we have to go in and tell it to try again, basically. So we have to hit the D key, and then suddenly it'll understand, oh, these are all basically instructions we don't care about. And then there's an add, there's a load, jump, load, so on and so forth. But you have to keep doing that over and over again because there's more and more sections. So you have to keep hitting that D button, go down, and keep scrolling. So anytime you see this RST38, you can kind of just ignore it. Game Boy uses FF to indicate, like, instead of like clearing memory with zeros, it clears it with FFs. So you can just ignore all of those FFs because that means that memory is not, there's nothing there. Usually that's what that means. So you can just keep going through. I'm not going to subject you to all of that process. So I'm just going to show you the interesting stuff. So it takes a while to disassemble all of the interesting parts, as I say. So we know from our memory map in the slides that we talked about earlier that we only really care about the addresses like 0000 to 7FFF, because that corresponds to the ROM section. And the reason why we only care about the ROM section is because that's the area that corresponds to instructions. So that's going to be the code, the logic of your program. It's going to be the logic of this Game Boy ROM. So if we need sprite data, or if we need background data, if we need any IO stuff, we can go and access that later. But chances are what we need is actually going to be in the ROM. So I pretty much have it set up for static analysis, but I do want to show you what the game looks like, so that way we know what we're looking for. So I have BGB debugger up and ready for us, and then this is its basically its debugger screen. So you can see the individual instructions, and then you can step through. You can set breakpoints, you can halt, you can reset, or you can just run. So I'm going to reload this ROM. So when you load the ROM, it will display a screen, but right now you don't see anything executing because I'm still in that debugger mode. So it's actually waiting for me to tell the debugger to advance before doing anything else. So if I double click in there, it starts executing. So we see that we have a mission that we have to complete. So our mission is to track down the rogue AI. Are you ready? So it's got this cool little intro. So it tells us that door needs a code, and then nothing else. So we know we need to find a code for a door. And then if we go to advance or do anything, those symbols pop up, and that's corresponding to my directional key presses. So when I press up, a little up triangle will appear. If I press right, a right triangle will appear. If I press down, a down triangle will appear. Left, left triangle, so on and so forth. And it looks like we've got a pattern going, and it says no good. So apparently the code for the door corresponds to some sequence of directional inputs. So we have to find a series of up, down, left, and right. We have to find that combo that will unlock the door. So we could spend a long time trying to brute force that, but that would take forever. It wouldn't be very effective, and we don't know which key presses are good. We only know once we submit all of them at the end. So we would have to get all 16 right, which is very hard to brute force that, and it would take forever. So we need to use our debugger and our disassembler, Ghidra. to basically figure out what that sequence is or find a way to bypass it. So we can go back to Ghidra. Now that we know what we're looking for a code, a series of inputs, and we can try and speed up this process. So we saw in BGB when we failed that check, it said no good, and it wants us to try again. And then it prompts us and we can put in a new input. So we should try looking for those strings that it's outputting, those words. So let's look for no good and see if we can find anything with that. So if you pull up your defined strings window, and the way you do that is you go to window and then define strings. And then it'll pull up on this right-hand side your defined strings. We see a lot of the words that we saw already. So like we already saw it say, my target is inside, I'm going in, you got it, boss, are you ready, so on and so forth. And then we see that no good message, and let me try something else. But we also see that worked, and first flag is. We never saw those when we were executing the program. That must be what happens when there's a correct sequence inputted. So we want to get to wherever this is being executed. So let's go look at first flag is. So first flag is stored at 2BD8. That's where those bytes are stored in memory. But we can also look at where it's cross-referenced. And so you can look at XREFs, which stand for cross-references for strings, and that will help narrow down what parts of the code you should be interested in, because we want to know where this is being spit out, what function actually prints that string, because that indicates a correct check. So I already went ahead and renamed the function. So originally this function was not called win. It was called like fun underscore 2b5d or something like that. But I renamed it to make it a little bit easier on you guys to keep track of everything I'm accessing. So we can go ahead and look at that cross-ref and then open the decompiler window on the right. So this is the win function. So we see that this win function calls a bunch of other functions. It grabs a value off the stack. It bitwise ORs it, does some other stuff, and then it prints, that worked, I'm in. And this is in well, this isn't in a while loop. It has some ending while loop, probably because Ghidra doesn't decompile it perfectly. So we can kind of ignore this at the end. So looking at this decompiler window, we don't get a lot of information. So we know that it's printing, that worked, I'm in, but we don't really know what else this win function really does. And so something that's helpful is looking at the function call tree of it. So you can look at the incoming references and the outgoing references. So you can see all the functions that win calls, and you can see those below, and you can see what function calls win. So we see that win is called by check. And once again, this is a function I renamed for convenience. So if we click check, we can see that it's setting some value to BA, some value to 3.8, some value to AE, so on and so forth. So we know that it's doing something there. But if we look down here, it says if local 3 is equal to hex 10, then call the win function. If not, call lose. So if we get here and 16 characters have been inputted, and the reason I'm making an assumption here. So I'm assuming that local 3 is corresponding to the length of the sequence, because I'm assuming because that character sequence was 16 characters, and then 16 in hex is 10. So I'm making an assumption there. So I'm assuming local 3 corresponds to the length of the sequence, because we also see that local 3 gets incremented here. So that's interesting. So either local 3 or local 2 is going to be keeping account of that sequence. But if we get there, we can either do, like, if we get through all of this, then we hit this. If local 3 is equal to that, then we call the win function. If not, we call the lose function. So we want to get here. We want to get to that win function. One of the first things you can try is patching. Patching is the easiest way to go. Or in this case, I'm not going to be patching the binary itself. I'm going to be changing values in the debugger during execution. But this is an easier way to go about it than to figure out the exact key presses, because I have less reverse engineering that I need to do if I just want to figure out how to patch it. So we need to make note of the win function, what address that's at, and then the check function, what address the check function's at. So the check function, we can see, starts at 2AA9. And then the win function starts at 2B26. So let's try something kind of quick and dirty, and let's try changing the program counter to the start of this win function. And the reason why I'm doing that is we may be able to actually skip all of the sequence checking logic and just have it print out the flag. That would be the best case scenario for us. But a lot of CTFs, you have to work a little bit harder than that, because they'll actually pull those values off the stack. But because they're doing it based on position, or key presses, sorry, there's a chance that they may not be stored in the stack. It may be, like, the flag may be displayed even if we don't have the right key presses. So I am going to reload this ROM. I'm sorry, you get to watch this intro again. So it's prompting us for the code, and then we want to jump to the win function. So that starts at 2B26. So we are going to set the program counter to 2B26. So it says enter new value for register PC, and we're going to enter that, 2B26. So now we are at the start of that win function, and we can verify by checking to see if 2B26 corresponds to the add df to the stack pointer, like the contents of df to the stack pointer. So let's go ahead and check that, and we get a similar instruction. So we've got add negative hex 12 to the stack pointer. So it's not exact. There may have been something that Ghidra did or the debugger did. So it looks close enough, especially if we look at the subsequent instructions. So the next ones are load instructions, and we can see the next ones are load instructions. And then an increase, and then let's see. Yeah, there's an increase HL. So we're definitely in the right spot. There may just be some differences with how Ghidra disassembles. So that's to be expected. So let's just go ahead and run it. Let's see if by changing the stack pointer to 2B26 and moving our execution to this point, we can just run it and it'll print out the flag. Let's see what happens. Oh, it's telling us that worked. So we successfully got into the win function because remember, it printed that worked and it prints something else. So yeah, it prints I'm in. All right. But we don't get the flag. We don't see first flag is like we expected. We see a bunch of zeros. So maybe things weren't as easy as we thought. Maybe it is pulling it off the stack and we can't just jump to the start of the win function and have it print out the flag for us. We need to succeed in that check. So the next thing we can do is we can go back and then go look at check again. So this is the check function. And then, so it sets some values here. And then it compares local 3 to hex 10. And then if so, print, go to the win function. If not, go to the lose function. So let's just try something quick and easy, see if it works. If it doesn't, we'll have to reevaluate and actually do some more reverse engineering here. So check starts at 2AA9. Let's see if we can just go to the start of check and see if it's actually just setting those character sequence values for us and pulling those from memory, like from the stack, for printing the flag. So let's just go to 2AA9 and see if that works. So let's try 2AA9. So now we set our program counter to 2AA9, so that's the start of the check function. And now let's just run it to see what happens. All right, it says no good. Let me try something else. So apparently, just running the check function, because we didn't input anything, we're getting into that lose sequence. So I am going to just reset. Sorry. There we go. That's what I wanted. I wanted to reload the ROM. And you'll see this again. Yeah, very exciting. I'm just checking something to make sure. Yeah. So if we went to the start of the check function, yeah, we're gonna get that. We're gonna call the lose function. We're gonna fail. So let's try one last like quick and dirty thing. Let's try and jump to where that win function is called before we actually enter the win function. So it gets called 2B, 1B. So let's try just jumping there. And I inputted the character sequence like a random one just to like if it's storing the values, like the number of characters, like the number of directional inputs, that way it'll be set to 16, just in case it's checking. So we want to go to 2B, 1B, I believe. Let's double check. 2B, 1B. All right. All right, and then let's run. So it's saying that worked. I'm in. Oh, and here we get the first flag is, and then it prints the flag. So that actually worked that time. So we're done. We didn't have to figure out that character sequence. We didn't have to figure out the left, right, up, and down. We could just change the program execution to go to a certain part of the program and execute, and then it would just print out the flag. So that's really interesting. That shows us the power of static analysis combined with dynamic analysis. There's almost always an easy way to do CTF problems. So like, especially for reverse engineering, there's usually an easy way and there's a hard way. And I am all for taking the path of least resistance, going for the easy, lazy solve. So that's what this was the easy, lazy route. Just changing the program execution versus reverse engineering the button presses and finding out what sequence you needed. So you guys basically solved your first Game Boy reverse engineering challenge. So this was from Square CTF 2017. I'm not sure how many points it was worth, but you guys now all have the skills to solve that challenge. And if you would have done Square CTF, you would have gotten that challenge. You would have gotten however many points it was worth. And so now you should feel confident in being able to look at a Game Boy ROM, load it into Ghidra with Ghidra Boy, narrow in on points of interest, and then using those points of interest kind of move back using cross-references, and then based on the cross-references, finding out where your win and where your lose functions are, and then manipulating the control flow using a debugger to get to that win function, and allow the program to set everything up for you so that way when you get to the win function, everything is like everything on the stack is in the right state. You're not corrupting anything. Thanks for joining. I'm going to be on Discord after the meeting to help out with getting people set up with Ghidra and Ghidra Boy, and using BGB or a different debugger or emulator. And then if I have time, I'll also walk through another CTF challenge, and we can either do it walkthrough style or it can be a collaborative experience like how it would be for a real CTF. So feel free to reach out on Discord, and I will help you as best as I can increase your knowledge of the Game Boy architecture and get more familiar with Game Boy reverse engineering.